It's a pleasure to be with you today. And actually, this talk is kind of an overview talk. I wanted to keep the level, say, somehow shallow, pedagogical. Actually, I will try to introduce some new material, actually, we're working on recently. It is not really a very focused research talk. It's kind of a broad talk, actually, of an overview of our recent activity. First of all, let me say from the beginning first, introduce myself. The name is Yanis Kourakis. I work in Khalifa University in Abu Dhabi and recently involved in the Space and Planetary Science Center. The work I will be presenting has been elaborated together with my good collaborators. In particular, I cite the local team, Kuldeep Singh, Steph Varghese, Hans Hoibrich, and Nikos Lazaridis. And let me thank all my external collaborators, actually, before I begin. So what I will try to discuss is mostly the topic of electrostatic solitary waves in space plasmas, give you a historical background and the basic information. I will try to present some, focus topics from our research activity, electrostatic solitary waves of various forms, and in particular, what I could call non-conventional or exotic electrostatic excitations. This is part of a longer talk, actually. So if time permits, I will also show you a few slides on phase-space holes and freak waves. If this is not the case, I will share my slides at the end, actually, so the audience can look at any slides I may have to omit during the talk, and then we will discuss and conclude. Think of solitary waves. I'm thinking of this in a general context. Obviously, these occur in a wider context beyond plasma physics. These are localized, coherent structures with remarkable properties, stability above all, a stationary profile, a stationary shape, stability against external perturbations. Physically, this might mean noise or interactions, collisions with one another. Physically speaking, these represent localized lumps of energy whose manifestation might be constructive. Think of signal transmission. What brings my voice and my image to you right now is an optical soliton, actually, that goes into through an optical fiber under the Indian Ocean right now, as my voice is coming to you. Or we might have a destructive manifestation of a soliton. Think of a tsunami wave, for example. Names exist in abundance. Historically, solitons have appeared as, say, pulses, king solitons, holes, electron or ion holes in plasmas, shocks, double layers for experimental plasma physicists, potential dips in, say, space plasmas, and so on and so forth. Surface oscillants, you name it. There's a number of different entities in this kind of nonlinear zoology, actually. This could either be periodic forms or non-periodic forms, pulses, which will be mainly my focus today, or they may possess some sort of internal structure, thinking of envelope solitons, actually. Now, beyond plasma physics, solitary waves have appeared in models in hydrodynamics. This is a widely cited picture from a nice paper by Mark Ablovich from Colorado from 10 years ago. And this is off the coast of Hawaii, actually. And we see solid interactions of what the authors of that paper succeeded to provide an interpretation for in terms of, say, interacting KP, for those who know the terminology, Kadomchev, Petviashvili solitons, actually. So you see these bumps, actually, that occur in the water, and they interact with each other, and they preserve their shape after their interactions. This is a satellite image of the Straits of Gibraltar, and you see this structure here, crest to crest. The difference is roughly 9 kilometers, actually. So you see a nice, say, train of solitons actually being formed, in this case, by salinity differences, actually. On the right, you have the Mediterranean Sea. On the left, you have the Atlantic Ocean, and one bumps into the other. It's a coexistence in a conflict between two different water environments, and this triggers these kind of stable forms, actually. Keep this figure in mind because I will come back to this a little bit later. These are internal solitons from the Andaman Sea, actually. Interestingly, this is a paper, say, depicting solitons. Here is a nicer picture from the same paper, actually. And it's interesting to think that this is the area where the tsunami struck, actually, years ago on the east of India. And you see this sequence of solitons, actually, of fronts, say, separated by, say, many kilometers apart, but preserving their shape as they propagate. So we see that we have generic mechanisms, actually, that, say, create and sustain these nonlinear waves, which obviously we expect to find in plasmas as well. Again, we see a similar structure, say, in the west of Africa, and you see these cloud formations, actually, which resemble the structures that we saw earlier. What about plasmas? Just to justify my presence here, actually, what we find in plasmas is a similar situation. This is a very nice paper, actually, which I like to cite in part because of the observations. Keep this figure in mind. I will come back to this electric field bipolar form that you see. You see a coexistence of a negative and a positive pulse in the electric field. And in the same time, this is detected in the same time as a bump in the velocity, as you see. So this was one of the first, actually the first, in detections of what people traditionally call ion acoustic solitary waves, actually, what the authors called collisionless shocks. Sometimes we get lost in translation, actually, in this business. Practically what this team by Lorenzo Romagnani did, supervised by Marco Borghese in Belfast, was that they used an ultra short and very powerful laser, actually, to shoot a target. I think it's a golden target. It's a very expensive target. Somehow the target melts, so to speak, and it generates a cloud behind, and this is what is the plasma, really. And what they detect is protons. That means, practically speaking, the ion density, and then the electric field. So what their proton diagnostics measurements, a technique allows them to do is to detect the electric field and then the proton, say, density and velocity, actually, so to speak. And you see that they see similar structures to what we saw earlier in different contexts, in, say, hydrodynamics and elsewhere, actually. Again, in plasmas, in the same laboratory with the same laser a few years ago, I participated to this study here, which was very interesting, led by Gianluca Sari this time. And what we detected, we explained as actually phase-space electron holes, actually, which is a different topic. I will come back to this a little bit later. What was an interesting thing is that the plasma that is created during these experiments is far from being in a Maxwell-Boltzmann distribution. So it's time I introduce part of the, say, potential building blocks of comprehensive theory for this kind of waves, which would be an electron background, which will not be Maxwellian. In this case, we used what is widely used in space, kappa distributions, and we found that the observed structures were a nice fit to the theory for a kappa value of 4, which means a strong deviation from the Maxwell-Boltzmann distribution. I'm still in the introduction, let's say, part of the talk. What we also saw was the spontaneous generation of these structures, what I will call a soliton, and I will explain why I call this a soliton, is this bipolar form that you see me highlighting with my cursor now on the bottom right, which is generated spontaneously in particle in cell simulations actually of say plasma expansion into a different medium. So from vacuum into a different medium. So you see that's bipolar forms that we observe in space, as I will show you in a few minutes, generated in numerical experiments actually. What about space? What about space? What happened in years ago, which is interesting, is the whole thing started with Northern Lights. Northern Lights is precisely what you see as my background right now behind my face, as Dr. Pandit Kumar actually observed earlier. So I'm happy to share this Wikipedia page because I find this to be very well written. Actually, it says that the auroras, this is called the aurora, or the Northern Lights in English. Auroras are the result of disturbances in the magnetosphere caused by the solar wind. These disturbances, I'm just reading the Wikipedia entry, are sometimes strong enough to alter the trajectories of charged particles in both solar wind and magnetospheric plasma. These particles, mainly electrons and protons, precipitate in the upper atmosphere, the thermosphere or the exosphere. So what really happens there is that the northern lights are visible near the poles. We have ideal conditions to observe, say, the aurora near the north or the south pole, and it bears different names depending on, obviously this has been observed even for many years, and centuries ago people would think it was a divine manifestation, it was a will of God actually to say make this nice kind of phenomenon in the sky, etc., etc. We know today that this is a real uh, plasma actually phenomenon. So naturally, this was the first region where humanity sent satellites to probe, say, what is happening in the magnetosphere. This is in the boundaries of the ionosphere, as a matter of fact. This was one of the first satellites in the 70s, the S33 satellite, which could detect one component of the electric field only. And what one of the first papers that ever appeared showing solitary waves in the magnetosphere is this one, which used the term double layers in the say in a sense in a meaning which is slightly different from what we say use today as terminology. A few years later, actually, Witt and Lotko, based on the same data, presented what they interpreted as a pairs of ion acoustic shocks. That's what they call those. I want to keep the notation, the jargon, till a little bit later. So you can call this whatever you want. What they thought they observed was a pair of pulses, which you see here, but you see this is kind of elongated. It's a very interesting distorted pulse actually, and then the electrostatic potential looks like this. It's kind of flat. So it's interesting to see that as early as in the early 80s actually, based on data from the 70s, you could see this structure, which I would like to discuss a few slides later. Electrostatic solitary waves appeared as a name later, for the first time in this paper by Temerin, actually, and then the history began. So this is how we somehow realized that electrostatic solitary waves are just everywhere in space. What we see on the left of the screen is a picture from the cluster mission. Cluster is what the name suggests, actually. Cluster was a cluster of satellites, not just one. I think there were 4 satellites. So basically they were trying to triangulate, say, detect different components of electric fields and trying to figure out what different components of the fields in the plasma actually were locally. And you see this interesting thing which I would like you to keep in mind for the rest of the talk. First of all, you notice there's a bipolar form here that goes first up, then down. It's a different polarity from the one I showed earlier. And you see this curly kind of structure here. What you see is the, say, kind of side bumps on the electric field being formed. This is interesting. On the right side, you see kind of more conventional, say, solitary waves. So this is um, say, bipolar form of the electric field, which is clear in this, say, satellite observations on the right. I think those come from the FAST mission, FAST, the FAST satellite. Interestingly, and more recently, actually, we have been observing electrostatic solitary waves of the opposite polarity from the previous slide near Saturn. This is a detection from the Enceladus. That's one of the moons of Saturn. So this is what is being detected by the Cassini mission, for instance. And much later, which is something we are involved in right now, also in the in Mars environment. I will come back to this in a few minutes. What we see often is the existence of, say, different polarities. You might see this bipolar form that goes up then down, but in the previous slide you had down then up. We know today that the different polarity is related to the dominant plasma component, actually. The faster solitary waves, which are due to, say, electronic disturbances, disturbances, as opposed to slow ion disturbances, will be of one polarity, and lower, say, speed and frequency phenomena will be related to the ions. So the polarity will be inversed. So in general, we expect to see more or less this situation, let's say having a pulse in the electrostatic potential. Remember that we are working in the electrostatic approximation. So minus nabla phi is the electric field. In one dimension, it would be minus the derivative of phi. So take the derivative. It's a very simple calculus exercise. Take the derivative of the blue curve, multiply by -1, and you get what appears to be a bipolar form, you see at the bottom. So the electric field as a bipolar form is related to a pulse-shaped electrostatic potential. If the pulse points upwards, then the electric field will have an opposite polarity, obviously. If, on the other hand, the electric field has a monotonic form like this, which is what we call nowadays a double layer, or laminar shock, actually, for what that matters, then again, take the derivative, multiply by -1, and you get an electric field which looks like a monopolar form. Obviously, what happens in space is that they detect the field and they work reverse gear. That means they integrate, multiply by -1, and observe what the theory is supposed to predict. So what kind of theory would give me these kind of shocks? I have to apologize to part of the audience who, as I realize, is very familiar with this theory. I promised to start at a bottom level, so it will be as simple as possible. Actually, what I'm calling here a T model is a cold ion fluid model for the ions, just adding non-Maxwellian electrons, actually, just to add a little bit spice, say, to the theory. But otherwise, this is the good old model of the 1960s, actually, for collisionless shocks, as they called it, back then proposed by Sagdev, Vedenov, and co-workers, actually, in Russia. We have the continuity equation, we have the momentum equation. I'm skipping thermal ion effects. I'm keeping things as simple as possible. And I have Poisson's equations. Actually, we see the first contribution for the ions and the second contribution for the electrons. The electrons are assumed to be at equilibrium, so they're fast. They do not, they just follow, actually, the ion dynamics. I attended a conference once, and somebody was very, I would say, graphic in their interpretation. They said it's like mosquitoes following cats. So if you're interested in the cat dynamics, you will not bother about the mosquitoes. The mosquitoes are the electrons here, and these are a cloud, let's say, at equilibrium. Obviously, this is a dimensionless model. Just for the record, I've scaled the ion density by the equilibrium density, same for the electrons, the fluid speed by the sound speed, naturally, and the space variable by the Debye length, actually. and the time variable by the, say, plasma period for the ions. What is the first, um, say, byproduct of this theory, simple as this sounds, actually, is the dependence of the say dispersion law on the non-thermal, non-Maxwellian character of the electrons. So we see that the phase speed is somehow slower, actually, if we consider smaller values of kappa, which means a deviation from the Maxwellian. And this agrees with what was predicted, say, many years ago, back then, with a motivation which lied in an experimental, say, plasma observation. Again, what about solitary waves? I mentioned nonlinear waves. Solitary waves need nonlinear analysis to be studied. I'm skipping the gory details here in the algebra. Again, I trust that part of the audience is familiar with these details, actually. What I really do is that I anticipate a stationary profile, say, for my excitations, a pulse, so to speak. Let's say the pulse is moving at a velocity. Traditionally, the velocity is scaled by the sound speed. So by analogy with acoustics, we call this the Mach number. Sometimes this term is not just used, it's abused in literature. This is the Mach number, provided that on condition that the denominator is the true sound speed in a given system. But remember that the sound speed will depend on the plasma configuration. So a word of caution here, do not use this letter, this symbol M, too lightly. Actually think twice before using this. In any case, what one can do is to lead from say the fluid system towards a closed equation for the electrostatic potential, which is like here, right here, which mimics classical mechanics. Let's say what was a real success of this method, the so-called Sagdev method. And again, the word is abused, I would say, and even Sagdev's name, as Rolf Sagdev himself said once, is abused in this sense. It's somehow general nonlinear dynamics, phase space method. It gives me the potential, think of the potential phi as being displacement, say, in space, and psi, which is a space coordinate, being time. So this would be a kinetic energy term for a mass being 1. So it looks like a kinetic energy plus a potential energy being equal to 0. So it's like having a ball, a billiard ball, actually moving in a nonlinear potential, actually. And the potential is right here. The first term is the ions, and the second term comes from the electrons, actually. Once we plug V inside this equation, we can integrate numerically and then find phi. Once we find phi for given boundary conditions, we can substitute inside the equations for the expressions for the ion density and for the ion fluid speed. And this gives me exact solutions, actually, which is what I see here. Keep in mind that the root of this potential, which is right here, this root there, which is 1 in this, say, normalized graph, is taken as boundary condition in the numerical integration. That means that the root here represents the maximum of my solitary wave. Keep this in mind. By the way, one more byproduct of this analysis here is the dependence of the region of existence of solitary waves. You see, for Maxwellian electrons, Maxwellian means a very large kappa, infinite kappa. This theory predicts electrons between Mach 1 and Mach 1.58. This is the actual Sagdev theory of the 60s. What happens is that this limit actually shrinks down to nil here for smaller kappa. So for kappa equal to 4, for example, which is a typical situation in space, you will see solitons between, for instance, 0.1 and 1.4. Be careful, between 0.9 and 1.4, some people say, Google that, and you will see plenty of papers saying subsonic solitons found in this or the other kind of plasma. This is not true. Whatever lies above the red curve represents the sound speed for the given kappa value. So the solitons will live above the red curve. The solitons will always be superacoustic, supersonic, except the sound speed goes down. So in reality, the yardstick goes down, the threshold, the sound threshold goes down and the soliton is superacoustic. Okay, so keep this in mind, this pulse. Once we have this solution for phi, we can obtain all the state variables, the electric potential, top left, the electric field, top right, the density number for the ions, and the fluid speed, bottom right. So we see that this is a very simple theory, and still, simple as it looks, it's a very realistic theory that gives me wonderful predictions, actually. I hope you can see a very crude movie we made a few years ago with Sébastien Guisset, who visited me from France. He's in CEA right now, and he's a wonderful researcher, actually, in plasmas. What we did was provide fluid simulations of this system just to test the stability. The SACDEF theory gives me static predictions. It gives me what the form of the excitations will be, but nobody guarantees theoretically, and this has not been studied yet, that the propagation will be stable. So this is, we somehow investigated through the simulations, and nobody guarantees theoretically that, say, interactions will be survived. What you see here is solitons interacting with each other during the SACDEF model. That means that what we did was to use the predictions of the SACDEF model as initial conditions, try to enter those solitons into collisions with each other, and try to see if they would survive. You see that aside a little bit of numerical noise, actually, the curves remain intact. Top, you see the potential, electrostatic potential, and at the bottom curve, you see the electric field structure. So now this is what this model gives us, and in a more complicated plasma configuration, you expect to have more exotic, say, phenomena. So this is what I'm about to introduce right now, just to advertise a little bit of our recent work with my good collaborators, Bharati and Amar Kakad, and Hari Krishnan in the Indian Institute of Geomagnetism in Mumbai. Actually, we use this simple model to provide an interpretation of electrostatic solitary waves in the Martian magnetosheath, actually, which is, in the best of my knowledge, the first, say, observation, published in a refereed article, actually, of solitary waves on Mars. And this has just been accepted, actually, last week. Should appear in Astrophysical Journal. So this will probably be my next talk next year. What happens if we have more components in the plasma? Something very interesting happens. 10 years ago, it looks like this theory has given a lot and has given all it could give. I know that many of you have used this theory as student projects, and a number of papers have appeared, actually. So it looks like it did not have anything more to give. See what happened in 2012. Ashasha, Alexander Dubinov, and Dmitry Kolotkov actually realized that if I had a few ion species to play with, in this particular case, they started with 5 different components in the plasma. They tried to create this strange topology that you see here, which leads in a phase-space topology which looks like this below. That means what I see on the left is the standard phase-space topology from the SACDEF problem. What I see on the right is a more complicated situation that corresponds to this, which is not what they call supersolitons, actually. Supersolitons is a very interesting term. It is borrowed from material science. It's been studied in materials earlier, which means that if you have a situation when the root can jump from a certain point here up to there, all of a sudden you have a sudden rise in the soliton amplitude, actually. I will show you a couple of plots in a couple of slides later. But what the qualitative thing to keep in mind is that instead of having the standard electrostatic solitary wave that you see here, which comes from the root on the left, what they showed was the possibility for existence of these curly structures that we see here, which is exact. It's a numerical solution of this SACDEF pseudo potential energy equation, actually. Then they used this theory to explain, say, observations of these kind of strange solitons that had been seen in, say, sulfur fluoride argon plasma earlier. And we picked up the idea with Frank Verheest and Manfred Helberg. That was 9 years ago. Time flies, as we realize, to show that this is possible in 3 species plasmas. Actually, you do not need to go too far. You just need a little bit of complication in your plasma. And you see that if you have the look at the black curve to understand what the point is. The maximum, the root is there. So the soliton amplitude here will be roughly 1.2 in these units. Look at the red curve. The red curve gives you the maximum, say, value of that amplitude. And all of a sudden, if the red curve becomes the blue curve, you've lost your root. The root goes all the way up to 5.2. So the blue curve gives you a root, which is all of a sudden the soliton amplitude multiplied by a factor 2.5. This is what deserves these structures the name supersolitons or super solitary waves. But also the qualitative aspect is that you get a distorted kind of solution here. Look at the electrostatic potential, what it looks like. And then when you differentiate, you obtain this curly structure for the electric field, just to make this presentation a little bit interesting for those of you who thought I was, say, presenting old material of the 60s, which was the case in the first few slides, right? What we did then, we tried to launch the same idea working with dusty plasmas, actually, dust ion excitations and non-Maxwellian electrons in the background. Again, you see this supersoliton generation for certain values there. And an interesting system, you will see why this is interesting. And the simplest one so far as I know, was ions and 2 types of electrons in the background. This is a typical situation in space when you can have colliding electron clouds actually, say, coexisting in the magnetosphere. And you see that you can have this nice supersoliton structure, which is, say, predicted theoretically. Now, is this relevant to space observations? We realize, and we spoke to Jolene Piquet actually after that time, we realized that they were observing this kind of solitons for years without realizing that it was not a train of solitary waves, but this was a different structure actually. Which is right there. So we actually do observe supersolitons in space. We also observe these elongated structures, which were later called as, say, flat top solitary waves or flat top solitons. These elongated structures here, you see, which look like the bipolar form, but with a flat region in between. So this is, again, a different kind of solitary wave. Now, how could these be combined in one model? Here I'm advertising our very recent work actually of say these last few weeks, and actually I'm somehow converging towards the end. I think time flies, so I will try to conclude in a few minutes. What we discussed recently was the coexistence of 2 different types of ions, say in a plasma, thinking of a typical situation in the Earth's magnetosphere, for example, when you have, say, somehow an interaction with the solar wind coming clashing with towards the magnetosphere, and actually this is in part the role of the role of the ionosphere actually to protect this planet from the solar wind. Now, what we see in this 2-ion model is, look at the green curve. And the green curve is what would give you a typical solitary wave. Solving the green curve situation numerically gives you this nice pulse. You see the green curve I'm highlighting right now and I'm pinpointing. And then this leads you to this bipolar form for the electric field. Now, increase the propagation speed a little bit more, say by 2% of the sound speed. You get the red curve, which looks hardly different. One might say, what's the difference? What's the real difference? It turns out that the topology of the curve leads to this flat top situation that you saw earlier in observations, the red curve, and the red curve leads to these elongated kind of bipolar structures that you see in the electric field, increased by just a little bit more look at the velocity numbers, actually. The difference in the sixth decimal digit is that actually the seventh. And this elongated structure shrinks slightly, goes smaller, more localized. So I get this structure, and all of a sudden I obtain the blue curve, and the blue curve leads to supersolitons. So supersoliton is obtained here, and this is the electrostatic potential, and this is the electric field. So you see that we obtained successfully what's been observed in space, actually. What seems to be and what should be taken home from this presentation, what seems to be the crucial factor actually for the supersoliton generation and for the flat top soliton existence is the cool electron concentration. What we discussed here, what we used as a model was two different ions and two types of electrons, Maxwellian, not even non-thermal, Maxwellian, simple, but at different temperatures. Look at the green curve, and the green curve is in both sides. You see the top panel here, top right, gives you the situation when, say, there is no cool electron. So two types of ions and just Maxwellian electrons. And you see that for all these curves, you only get solitary waves. That means single roots, simple roots. So nothing exotic here. You switch just a little bit, 0.01% of the electrons could be at a different temperature. And all of a sudden you give the red curve and the blue curve the right of existence. So what this leads to, as we saw, is the existence of supersolitary waves, as we see here, or of flat top solitons, actually, as we see in the red curves, actually. Okay, I think this brings me closer to the end of the talk. There is a lot to be shown, but I'm afraid I will have to cut it shorter here. Just advertising actually a little bit recent work by Mark Akkad in Mumbai. They were inspired by our paper with Frank Verheest and Manfred Helberg, just ions and two types of electrons in the background. That's why I told you it's a typical situation to look for supersolitons. And what was very interestingly, what they obtained, what they observed was, I hope the movie will work. They saw for the first time numerically the spontaneous generation of supersolitary wave. Actually, they tried to launch a plasma on the computer, actually integrating the fluid equations with specifically the values predicted by our paper, actually, for stable supersolitary waves to exist. And they see that there is this structure which arises spontaneously after a while. This is slightly supersonic. Remember the diagrams in my previous slide, they were just 10% above the sound speed. So naturally there are sound waves following behind, just lagging behind. This is not numerical noise. This is just linear wave packets actually behind. But you see that the nonlinear structure is stabilized somehow. And one might wonder, how does that compare with the theory actually? So very wisely, they compared the numerical result from the simulation with the red curve to the theoretical result from our paper, actually, with Verheest and Helberg, which is the blue curve. And you see there's a fantastic, surprising match, actually, agreement between theory and experiment. Obviously, the next logical question would be, fine, are these normal mode, so to speak? If I take a supersoliton and I force it to enter into a collision with a standard soliton, you see, so what you see here, let me press the pause button, and I'm afraid this has to be the last slide for today. If I press the pause button, what you see on the left is actually what is propagating towards the right in this panel here, which is the left panel, moving to the right, towards the right, okay? This is a supersoliton, which is stable by now. It's a stable form. In the same time, on the right, you have a standard solitary wave, which again is propagating to the left. And they have used this highlighting, the red frame and the magenta frame, you see, before they enter into collision. So right now we need to brace for impact. you see at the bottom the two solitary waves coming closer and closer and closer. Let me see if I can catch the moment of the collision, actually, right there. So one is about to bump through the other. Let's see what happens. A phase shift as with normal KdV solitons, and then again, the question is, will they stabilize themselves? Now the collision is over. What about their shape? Did they preserve their shape? Who knows? Let's see. What then Kakad and co-workers did, they tried to look at the form before and after the collision, and you see that the shape is preserved perfectly, actually. So I think this is just a good time for me to press the pause button and stop the presentation. Actually, there's a couple of slides I'm omitting here, which I'm asking you to have a look at, and please do not hesitate to contact me if you have any questions on this material. I'm just jumping back to the first slide where I hope I have my electronic email. Yes, that's correct. So thank you. Thank you for having me here today, and I'm happy to answer any question on the chat box or orally. Thanks.
So now the talk is open to questions. Any question from the audience? Please raise your hand. Dr. Karmakar has a question. Professor Karmakar, please ask.
Yes. Okay. So thank you for nice and informative presentation. So you have given an overview.
Thank you.
So
Thank you.
I have a question regarding Shokdev potential approach, pseudo potential approach. So is it applicable for dissipative systems, non-conservative systems?
That's a nice question. I would say I'm answering personally, actually. There is not much in the theory, in literature, actually. If you find a book by Karpman, it's a very nice coincidence. I had Antoine Brett's presentation earlier. Karpman published a book on shocks and collisionless shocks many years ago, and they discuss this aspect. They discuss the dissipative picture of the Shokdev theory, actually, but it has not been discussed much, to be honest. It can be applied, but it is not really. Remember, the Shokdev picture essentially relies on
Spring mass system, classical spring mass system, conservative system. Yes, right.
Exactly. You see, so you have a conservation, an energy conservation situation, which is given here. So if you add dissipation, you should have to have some loss term, I would say.
Yeah.
So in a sense, this would work nicely. I think what you have in mind is these, say, Korteweg de Vries theory and everything, and this would work nicely here, but not through the Shokdev picture. Yeah, that's a very good comment, actually, Dr. Karmakar.
Okay. Thank you, sir. Thank you, sir.
Thank you.
Any other question? Some people have commented about the talk being very informative, and two participants have some questions.
Yes, please go
Yeah,
ahead.
Mrityunjay, please ask. Mrityunjay Bawari. You raise your hand, please.
Okay, hello. Can you hear me?
Yeah.
Yep.
Sir, I want to ask how you obtain the curve between the Mach number and the K value.
How I obtained the relation between the Mach number and
K, kappa.
And kappa. I see. That's a nice question. I like this question. Thank you. actually, thanks for giving me the opportunity to mention this here. I think you refer to this fact here, correct? Can you please confirm? This is what you mean by your question, right? So what we see in the, it's not really the Mach number. What you see in the red curve is a simple requirement of the origin here, 0.0 being a maximum. What you expect from nonlinear analysis for this theory to work is that you need that phi equal to 0. You need to have a local maximum. Think of standard calculus. A maximum means a 0 first derivative and a negative second derivative. The negative second derivative gives you precisely the condition that the soliton speed, or the Mach number, if you will call it this way, should be above the red curve. For different values of kappa, you solve this equation numerically and you find different points. So this gives you the red curve. So this tells you that the Mach number, as you called it, has to be above this value. This comes from nonlinear theory. Qualitatively speaking, in physics, linear theory will give you the sound speed. So you work out the linear limit, you found the phase speed of linear waves by coincidence, which is not a coincidence. It's a remarkable manifestation of how algebra explains nature, actually. If your model is a good one, you find the same expression. So the linear phase speed, which is actually the sound speed, in the kappa theory gives you this expression here. And just for details, I think I have the reference of these paper right here. I thought it was also on the abstract of the talk. For the upper value, in case you're interested, which is the blue curve there, again, this is a function of kappa. We wanted to make sure that all of the state variables will be real. You see a square root, again, standard algebra, standard calculus. You have a denominator. The denominator must not be 0. You have a square root. Whatever is under the square root should not be negative, of course. Otherwise, you will go complex. You don't want this. So you force this quantity under the square root to be positive, which means phi has to be below some value. Plug that phi into the expression of the potential, and you want this value to be above the axis. You would not like a situation when your density becomes complex, that because you lose your ions, that means your model is not a good model anymore. This gives you, you solve this equation here, which I just mentioned. That means that the point when this denominator goes to 0, which means the density goes to infinity, and this is what people call the infinite compression limit for this reason. And the infinite compression limit, when you lose the reality of your state variable parameters, actually, gives you the blue curve, the upper curve. So your soliton will have to survive, will have to live between these curves. Your Mach number, if you wish, has a lower bound, which is the sound speed, has an upper bound, which is given by this infinite compression limit. Okay, I hope I answered the question, if I understood it properly. In any case, I'm happy to discuss anytime by email later if you would like more detail on that. Okay.
Ajaz Mir, you were having some question. Ajaz Mir. His question is this kappa the Jacobi elliptic parameter?
Yes, I just saw, yes, it's not the answer. I just saw this on the chat window on my right. This is actually not the Jacobi elliptic parameter. What this kappa is, it came into the picture through this expression here, which I'm showing you. Now, this kappa function that you see here is a product of integrating a particle distribution function, which is not Maxwellian. This is a particle distribution function which was launched in the middle 60s. Actually, what happens with the Maxwellian theory is that the Maxwellian is basically a Gauss function in the velocities. So think of the Maxwellian, the very basic physics, when you learned about the Maxwell-Boltzmann equilibrium. For very large V, it decays down to 0. It decays exponentially, so to speak, in V square. So you find think of standard Gaussian theory in statistics. It's what, 2.6%, I think, is above the first 97% of the velocity arguments. So most of the particles are centered around the thermal speed. That's the interpretation of the Maxwell equilibrium. And they realized in space in the middle 60s already, that's 55 years ago, that things do not work like this. In space, they detected electrons and particles with a very strong superthermal component. That means for very large, say, values of the velocity, you had a power law. You wanted this to decay as 1 over v, some exponent, but not an exponential decay. So the Maxwell picture did not work. And one of the functions that seemed to work is the so-called kappa function. It has nothing to do with the Jacobi elliptic parameter. It's a coincidence I'm using this symbol, okay? And recently, actually quite recently, less than 10 years ago, there was a book by George Livadiotis, the kappa distributions and their use in space plasmas. So this is a whole new world, actually. Kappa distributions give you different behavior in your plasma waves, whether linear or nonlinear. Again, I'm happy to give you any detail to any extent you would like by electronic mail, if you wish. Okay, but the answer is no, this is not the Jacobi elliptic parameter, actually.
So let's thank the speaker.
Thank you.
Thank you, Professor.
Thanks
for such a wonderful talk, and it was a nice covering every aspect of soliton and leading to supersolitons, and it was a very systematically planned talk.
Thank you.
Thanks for such a wonderful talk.
Thank you.
Thank you for acceding to my request and coming here for the talk. Thank you.
Thank you. Thanks for having me.